Hello and welcome back to this series of videos about rebuilding a Rolls-Royce Merlin engine. I'm going to talk about something slightly different this time before moving on to going through rebuilding the wheel case in the next episode. During its service life, the Merlin was generally very good at doing what it was designed for and didn't really have very many problems. The two main exceptions to that are the negative G effect on the float carburetor, which I'll talk about in another video, and another thing which was called skew gear failures, which some of you will have probably heard about and read about. This term refers to the failure of the gear drive to the common shaft driving the two magnetos on the engine, so although for redundancy they use two ignition systems, they are both coupled to the same shaft. In the summer of 1942, they started to see more of these failures, and a lot of them were experienced by the Spitfire test pilot Alex Henshaw, who writes about it in quite a bit of detail in his book called Sigh for a Merlin. And in this video, I'm going to go through the lengthy process by which they worked out what was causing the failures and how they went about putting it right. So this is the magneto drive shaft. One mag goes into that side, one into the other side using coupling shafts, and one of the skew gears is machined onto this. This is the bronze skew gear on the wheel case vertical drive shaft, and this is a component that actually used to fail. The two gears mesh like this, and I can show you the operation of these on the lathe in a minute. The upper vertical drive shaft has a bevel gear onto the main drive shaft out of the back of the crank, and this gear here is the first stage step-up drive for the supercharger. So the first thing I'm noticing here is there's a certain amount of push. It's pushing the thing towards me that way. And the greater the torque you carry through these gears, the more that loading is going to be. And also you can see, or I can tell that the teeth are obviously rubbing together as they go around, so it's slightly different to a set of straight cut gears. You can kind of see that if I push the gear through there, the action of the teeth sliding against each other. These skew gear failures had started to increase as early as 1941, particularly after the introduction of 100-octane aviation fuel, which enabled them to run more boost, and obviously the engines were making more power. The significance of this wasn't really apparent to them at the time, but they started to have a look at the form of the teeth and the finish. They weren't actually grinding gears at this point in time, they were machined, so they put better quality control onto both of these gears. They also then introduced an oil bath underneath this gear, driving the magnetos, just to provide more consistent lubrication, and also an additional oil feed to the top of the wheel case. Originally, the magnetos were driven with this vernier coupling on each side of the engine. And just as an aside, it's got a different number of splines on that end to this end that goes into the magneto. So when you're timing the mags, if you take it out, turn it one tooth, put it back in, then you actually get a very small, I can't remember the number, but a very small amount of timing variation. And the camshafts are also timed in the same way. So they went over from this solid metal coupling to one with a rubber component in it, and then down inside there there's a spline which has allows a very small amount of angular movement. So if the rubber component fails, it still drives the magneto, but this basically allows some torsional movement. And it was in 1942, when Alex Henshaw in particular started to get a lot of these failures, that the chairman of Rolls-Royce, Ernest Hives, was tasked with finding out a bit more about it. One of the first things they discovered was a correlation between the backlash in this pair of bevels down here and the backlash in these gears. So what I mean by backlash is play in the gears. So you don't want these two bevels here meshing really tightly. You need to have a certain amount of what you can hear there, which is play in the gears. And this is achieved by this washer that you can see here, and also the washer on this shaft here, which goes underneath the bearing. And this enables you to set that gear and then set that gear there in very specific positions. You need a very small amount of backlash. And what they found was, if the backlash on these gears was greater than on the Skew gear set, it was causing damage to the Skew gear. The reason you want a small amount of backlash can be for various reasons. You don't want the gears pressed tightly together, because not only does it tend to push the lubricant, the oil out of the way, it also generates heat, it makes them harder to turn, so it's obviously losing power effectively if your whole gear train does that. The reason you don't want too great a clearance in them is a bit like, if I just put a very small amount of movement in there, I can hit the two teeth together like that. And that's about all I can do. If I pulled them further apart and started to do it, you can hear it's louder. It's a bit like taking a bigger swing with a hammer. And the reason it's quite important on gears, particularly in an engine, is with nearly all engines, the cylinders fire sequentially in some way, which means that basically none of the cylinders fire simultaneously. So let's say a cylinder on this particular crank web here, crank throw, fires. It's going to put a bit of a twist into the crankshaft, which then springs back again, and then it'll spring in a different, well, not a different direction, but the same direction from somewhere else along the crank. This effect is known as torsion or twist. And with the cylinders firing one after the other, you get a torsional vibration set up, which is what I was showing earlier. So it tends to make the teeth do this. These teeth on the bevel gears are hardened. The magneto Skew gear teeth are also hardened, but this bronze gear isn't, and this is going to be the one that's the most susceptible to wear and damage. Rolls-Royce then discovered that the backlash in these gears had to have been greater at some point because of the damage that was occurring to them. So they had a look at the crankshaft to see whether it could have been moving, and then pushing that gear partially out of engagement with this one. So the crank is held in the engine longitudinally by this centre main bearing, and it's literally that bearing surface on either side on this centre journal. It's located, which is standard practice on again, nearly all engines really. And there is virtually no, if I try and twist this, there's virtually no movement there at all. So there's just enough clearance down the sides. Let's see if we can see it down the sides of that thrust bearing shell there to give a small amount of clearance for the oil, and that's it, no more. So there's a minimal amount of movement there. So then moving to the front end of the crankshaft where we drive the propeller. There's the coupling shaft, which is designed to damp out some of the torsional vibration. And then the reduction gear pinion. The pinion is supported on two sets of roller bearings and is completely independent of the crankshaft, the only connection between the two being the torsion shaft. So what they eventually discovered was that because this roller bearing is located in the engine crankcase, and the front roller bearing was located in the reduction gear cover. And you can see how this goes together if you watch episode 7 of this series, that it required very accurate machining to keep the two in line. If they were dead in line, or the front bearing was a very, very small amount lower, the action of this splined coupling shaft in the middle would cause the crankshaft to push back. And if we return to the lathe in a minute, I can show you how this happens. Going back to the centre main bearing, the panel of the crankcase which this thing is fitted to, so the main centre part of the crankcase, was able to deflect under the force of the coupling shaft. And we're only talking about very small amounts. It was 12 thousandths of an inch, or about 0.3 millimetres. But an additional 0.3 millimetres of clearance in these gear teeth here was enough to cause the damage to the Skew gear. So I've got the coupling shaft set up to turn in the lathe. Here's the reduction gear pinion. I'll just put it on as it would be in the engine. Because there's a bit of clearance in the drive spline at the front here, I'm able to actually lift the back of the gear up and down, which is what we're talking about, of course. So it's whether the back of the gear is slightly higher than the front and vice versa. All the time it's sitting here on the lathe, gravity is pushing it down, which means that it's actually running slightly off centre. So if I run the lathe, you'll see that it moves forward. And then if I reverse the lathe, you'll see that it moves back again. And the greater the amount of torque being transmitted by the gearbox, and also the greater the offset angle from front to back of the gear, the greater the amount of force which is either pushing forward or backwards on it. In this instance here, we've got about 2 millimetres of movement and not really any torque going through the gear at all, of course, but that's enough to make it move. However, on the engine, we're talking about something more in the order of 0.002 of a millimetre of offset, but a very, very large amount of torque being transmitted through it, and that has the same effect of actually pushing very hard on the gear. They were able to prevent the coupling from pushing back on the crankshaft by maintaining the front of the pinion 1.5 thousandths of an inch higher than the back one, which is about 0.04 millimetres. And this was achieved by drilling out dowels in the joint between the casing and the crankcase. And if necessary, putting larger dowels in, basically, once it had been repositioned. And then it would always go back in the same position. Out of all the forced landings that Alex Henshaw had, which were caused by the Skew gear failures, the closest he came to not making it was probably this one on the 18th of July in 1942 at Willenhall, when he was flying Spitfire Mark 5 EP 615. Engine failures of this type can be a bit disconcerting for the pilot, because the instrument RPM and boost readings don't really change, so you're left trying to figure out what's happened and whether there's anything you can do about it, while all the time you're losing altitude. I've also heard it referred to as the deafening silence, for obvious reasons. In an interesting twist to the story, he mentions in his autobiography that he was contacted by Rolls-Royce some time later, who explained the basics of the problem to him that had been solved. But they also pointed out that all the engines were coming from one source and that they'd been assembled, in his words, the opposite way round, which would probably imply something to do with the orientation or the angle of the reduction gear pinion. But in view of the fact they hadn't been focusing on this issue previously, I strongly suspect that the increase in failures had more to do with switching over to 100-octane fuel in 1941, so the engine started producing more power and probably affected fighter aircraft more because of the way in which they'd be flown, rather than bombers which were cruising at lower powers for a lot of the time. Well, I hope you enjoyed this video. It really illustrates the complexity of the design process on something like this engine, and the great lengths they went to in the middle of a war to fault find on them and keep them flying. It reminds me of one of the most famous quotes of R.J. Mitchell, the designer of the Spitfire, when he said, "If anybody comes along and tells you something about an aeroplane that's so bloody complicated you don't understand it, take it from me, it's all balls." Except on this occasion, it was all very real.